Hello and welcome to this What's New video, presenting the latest developments in the NVH domain for ANSA and Meta of version 25.0.0. Let's start by have a quick overview on the new features. Starting with ANSA, NVH console is enhanced as it offers now a DOE and optimization studies for panel thickness and shape changes. A new connector is created that enables the connection of a fluid and a structure. And acoustic source excitations can now be defined. A modal damping per component could now be considered when performing system mode participation analysis. Plenty of enhancements at the field of statistical energy analysis. Concerning the new features in Meta, the Modal Model Builder is supporting now Abacus files. An extended support of PERMA's results is various tools. A new optimization method is available within the Modal FRF correlation tool. And finally, we have damping enhancements in Transient Response tool. Let's start to see every topic in detail. Within the NVH console, the Optimization DOE Setup interface facilitates an easy setup for DOE and optimization studies. With the variables such as the component panel thickness and the shape changes. Fast and accurate DOE and optimization studies as a result of the use of reduced models. For the purpose of a demo, you have a simplified track model composed of the frame, the body, and the bed, and this is how it's represented in the console. Under the Assembly menu, we select the Optimization DOE Setup. The interface is launched, where we observe the new tabs of the component panel thickness and the morph design variables. So we have just to select the components. In this case, I select the frame, and now from the frame, we should select the properties that will be used as design variables. In this case, I will use the longitudinal parts of the frame and some other transversal components of the frame. There are some options below to change the design variable limits, the minimum max value from both of the properties once they are selected. So I can increase, for example, and once I press apply, you will notice that the minimum max value will be updated accordingly. Having an initial value of 3, that can vary from 2.55, 2.7 up to 3.3. Please notice in the summary section on the right the selected DVs. Moving to the Experiments tab, we can select the desired algorithm to generate the experiments. The values next to the algorithm are the respective option for each selected algorithm. So if I scroll down to the algorithm, you will see that options become activated and can be tuned accordingly. We will simply use the first one, and just by clicking on Generate Experiments, we will get 20. It should be emphasized that a minimum of 10 designs must be selected, as required by the surrogate model of the response surface methodology within the ANSA optimization tool. As we can notice, the Create and Run DOE button is currently disabled because the analysis has not been fully defined, as indicated by the message. To extend the tool's capability, the Launch ANSA Optimization Tool checkbox will be selected to transfer the analysis to the ANSA Optimization tool. Please observe the renamed button. Changing to the Responses tab, we find all responses defined in the console beforehand. Let's select some of them, such as the mass delta, the response inside the cavity, and switching the objective type to RSS. Select a displacement response and define the minimization as an objective type. So now that these options are also defined, the button is enabled, and once I press it, a DOE study will be transferred to the optimization tool. Let's review then a completed run for 11 experiments. As you can see here, these have been run already, and they have been stored under the working directory. This is the working directory DOE Run 001. We can see here a list of experiments where each folder contains the results of the analysis that we have defined here. Additionally, the file with the design variables that have been used. Once the analysis is completed, the status symbol becomes green. Moving to the next tab on the RSM where an entry exists already. The RSM has been done by clicking on the new RSM and by selecting the Kriging algorithm. And let's move to the optimizer. Providing a name for the optimization and select the simulated annealing algorithm. As a method, either the RSM or the direct can be selected. By selecting the RSM, the optimizer will use the RSM functions that have been created before, and it runs faster. While by using the direct, the experiments will have to run once again, which is time-consuming. Let's get the RSM. These are the current settings for the optimizer, the responses that have been decided already. Constraints objective. We will keep the mouse optimization, that's the initial values for the optimizer. Next, let's confirm it and close this interface. The optimizer is already defined. Click on Start and as you can see inside the info window of the optimization tool, we get the results. So the new optimized response and the minimized displacement for the response on the frame 1 set direction point, also the change in the total mass. A pop-up window appears to validate, if desired, these results by running again an optimization task with the optimal values. Finally, the results will be compared with the optimizer. Skipping this process by press Cancel. In the Results tab, an analysis overview is provided with the help of various charts and graphs. Under the Optimization tab, the optimization runs are listed during the optimization process until the objective function is fulfilled. Continuing to the second enhancement of NVH Console, a significant feature has been introduced to connect the fluid and structure components easier and more efficient. As a result, the new FSI connector enables now the handling of cavity as a standalone component, the creation of multiple cavities, and easier model handling in general, and other extended modeling capabilities. Let's start with a simple example of two components: the full face of a body and its cavity. The components are already defined. In order to connect them manually, navigate to the Create menu, go to Connector and click on the new Fluid Structure Coupling. Then, just select both components, one after the other. The connector interface pops up, showing a predefined connector name and component's name that will be connected. An existing file can be indicated or a new one can be created by pressing the Calculate button. In this case, let's provide an existing coupling file and press OK to create the connector. By this, fluid and structure are now connected with the new FSI connector. And now let's explore the transition to a reduced representation. On the structure component, press the right mouse button, go to Representations, Binary Model Display, click the Create Update. On Display Model, an existing one will be selected by clicking the Load button and select the appropriate display file. On Coupling, the default options are kept. On Eigenmodes calculation, a predefined Lanczos method is selected. On Damping options, the default value of 0.02 is kept. Finally, on Nastran output, by keeping the file field empty, the current working directory will be selected. After the process is completed, let's review the created reduced representation where all needed files are listed. As can be seen by opening the FSI connector, the reduced coupling file has been created. That was the way that we need to follow in order to use the new FSI connector. Let's continue and find out how to update an existing old modeling. So in this case, we just have body frame and bed the body. As we can see, it's defined according old interface. Under the Custom menu, click the option Update Old FS Group Modeling. After the process is completed, we observe that fluid and structure are separated components and connected with an FSI connector. An acoustic monopole can now be defined within the Load Case Manager of NVH Console. Under the Loads tab, a new load of type press use should be created. And its characteristics have to be defined as well. Currently, the load profile is provided as the real part of the load. Finally, we see how the load is described in the FRF assembly tool within Meta. In case of submitting a frequency response analysis either to Nastran or Apillicis, then keyword ACSRCE will be written for the acoustic source. Let's review a predefined example. Navigate to the Load Case Manager and switch to the Loads tab. As can be seen, there is a new entry under the various load types, the pressure. The load is already defined and exciting the cavity of body. Responses are also defined at the body at different locations, and we can proceed by submitting an analysis. Under Assembly menu, we press Run. Switching directly to the results within Meta, we can examine the responses of velocity and pressure. And a quick look in the FRF Assembly tool can reflect how the excitation is defined. Last enhancement regarding the NVH console is the capability to define modal damping per component when submitting a system mode participation analysis with Apillicis FAST 103. Looking on the Apillicis file, we observe next to the component definition the keyword dampedval, hosting the component's modal damping. Also, we have to mention that now the option perm post-XTS is available by default, leading to export the damping matrices in OP2 file. Let's move to the respective example. For the purpose of this demonstration, the modal damping of the components has been differentiated on purpose. Let's review the components one by one to confirm the variation. Please notice the respective structural modal damping for the body, the frame and the bed. As we mentioned, the feature is available when submitting a system mode participation analysis. It's accessible by editing the current configuration. In this case, the job has been submitted already by pressing the Create Results button. The selected solver should be the Apillicis FAST 103, in order to perform a component mode synthesis. Bear in mind that the option perm post-XTS should remain activated. Otherwise, the damping matrices will not be exported. Let's review the submission file where the dampedval keyword is written next to every modal component. Moving on by loading the job results in Meta. Examining the results, such as the velocity, the pressure, and the system mode participation factors for the respective responses. And now let's perform a quick validation on the results by overlaying the total velocity response originated from the Apillicis FAST 103 analysis versus the complete system analysis. So, the results correlate perfect at the peaks as expected. Finally, a closer look to the modal response tool reflects how the analysis has been defined. Please notice the listed damping matrix that was requested previously and the corresponding setting that enables it. And by this, we completed the demonstration of all NVH console enhancements. In version 25, all functionalities related to statistical energy analysis have been consolidated into a single ribbon tab. A new checks manager has been introduced to ensure analysis integrity, and a graph view is now available for visualizing subsystem connectivity. To facilitate the plotting of SEA entities, the SEA toolbox has been added, allowing for a quick preview of subsystem characteristics. Additionally, four new entities have been included in the context menu within the database. Energy constraint, acting as a boundary constraint. Frequency domain. Noise control treatment. Power source. Also, two new material types are supported for the fiber and the foam. As we progress to meta enhancements, let's introduce the new capability of the Modal Model Builder tool to export a modal model in Abacus format. An additional option beyond the previous Nastran-only choice. Moving on to the second enhancement of Meta, we now offer extended support of PERMA's results across various tools including the random response, the modal FRF correlation, and finally the modal FRF bar chart. A new method has been implemented within the modal FRF correlation tool for optimum driving point selection. Applied to the selected potential excitation points, a plot is created to visualize the driving point criterion. By submitting the optimization process, the generated plot shows best point and direction that can excite the structure based on the DPC criterion. A vehicle's subframe will be used to demonstrate the new feature. Please notice the ALC points on the model. Some of these points are selected at attachment locations with the vehicle's powertrain and frame, while others are chosen at areas ideal for structural excitation using an impact hammer designed for modal testing. To become familiar with the model, we will quickly review the animated mode shapes. Next, we will proceed by invoking the Modal FRF correlation tool. The modes have already been loaded, with some excluded from the list to streamline the demonstration. 5 modes within a frequency range of 83 Hz to 234 Hz will be used. Under the Settings tab, various related options are available, such as the threshold value of the DPC used during the optimization. Switching to the Optimization tab, the driving points for the powertrain and frame are already selected. By pressing the DPC button, the criterion is calculated and visualized in a MAC plot. The driving point identification process considers both the excitability of the modes labeled as EXC value and the risk of double hits labeled as add-off. The x-axis corresponds to the selected nodes and the excitation direction. Returning to the Modal FRF correlation tool, we continue with the determination of the optimal set of driving points. By pressing the Optimize button, the process begins, using the same nodes as before. The generated plot, which incorporates the DPC criterion, displays the best driving points, including the excitation direction that excites at most all selected modes. And by this, let's move on to our latest enhancement in transient response analysis. It is now possible to apply modal material damping in a modal transient response analysis using the Modal Response tool, resulting in greater accuracy and higher correlation with a Nastran analysis. The modal parameter specifies a structural to viscous damping conversion method that uses solved modal frequencies as conversion factors. The parameters G, W3, and W4 are also considered, along with the matrices listed under the Matrices tab. Within the Modal Response tool, viscous modal damping is now available for transient response analysis. Under the Settings tab, a dedicated damping section contains all related damping options. In the Transient Response section, users can enable the modal parameter and define the structural and fluid parameters G, W3, and W4. In the current example, a simplified cabin model is excited simultaneously at 4 points at the bottom with a sinusoidal input. The response is measured at a structural point. The modal basis file includes both the structural matrix K1 and the structural damping matrix GK1, as shown in the Matrices tab. By enabling these matrices along with the modal parameter, we achieve excellent correlation with a modal transient response analysis solved using the Nastran solver. As demonstrated, the responses correlate perfectly. Thank you for watching and stay connected.